Imagine a time before time. Before light, before stars, before planets, there was nothing. But from this nothingness, our universe exploded into being. The Big Bang, scientists call it, a moment of creation that set in motion an epic story. We're going back billions of years long before our solar system existed. Picture a vast, cold and silent cloud. Not a cloud of water vapor, but a cloud of gas and dust. This cloud, a nebula, drifted through space. Within this cloud, a drama was about to unfold. The seeds of our planet, our solar system, were hidden within this swirling mass. Under the influence of gravity, this cloud would begin to collapse. Slowly at first, then faster and faster. And it's here, in this seemingly unremarkable corner of the universe, that our story truly begins. For centuries, humans looked to the heavens in wonder. The sun, the moon, the stars. These celestial objects inspired awe and sparked countless questions. In the 18th century, a new breed of thinkers emerged. Scientists and philosophers who sought to understand the universe. Among these pioneers was a German philosopher named Immanuel Kant. In 1755, he proposed a bold and revolutionary idea: the Nebular Hypothesis. Kant's nebular hypothesis was rooted in his observations of the natural world. He saw order in the seemingly chaotic dance of the cosmos. He observed that the planets in our solar system all orbit the sun in the same direction, and in roughly the same plane. This suggested that the sun and planets had formed from a single rotating cloud of gas and dust, a nebula. As it collapsed, it spun faster and faster, much like a spinning ice skater pulling their arms inward. This spinning motion played a crucial role in shaping our solar system. His hypothesis laid the groundwork for a new understanding of our place in the cosmos. Kant's ideas, while revolutionary, were largely qualitative. However, his work caught the attention of a French mathematician and astronomer named Pierre-Simon Laplace. Laplace, renowned for his mathematical prowess, saw in Kant's nebular hypothesis a framework that could be tested and refined using mathematics. In 1796, he independently proposed a similar theory, adding his own mathematical rigor and insights. Laplace developed a detailed mathematical model of a rotating and collapsing nebula. He demonstrated how gravity would cause the nebula to contract, its rotation to accelerate, and a disk of gas and dust to form around the central growing protostar. Together, Kant and Laplace's work laid the foundation for our modern understanding of the solar system's formation. Imagine that swirling cloud of gas and dust, a nebula stretching across unimaginable distances. It's cold, dark, and seemingly still, but within this apparent stillness, a drama is about to unfold, driven by gravity. Each particle of gas and dust exerts a gravitational pull on every other particle. Over vast distances and immense periods, this force begins to draw the nebula inward. As the nebula contracts, it begins to spin, gradually accelerating. This spinning motion counteracts the inward pull of gravity, preventing the cloud from collapsing entirely into a single point. This delicate interplay between gravity and rotation sets the stage for the birth of our solar system. As the nebula collapses further, the center becomes increasingly dense and hot. The particles collide more frequently, generating even more heat. This hot, dense core is the nascent sun, a protostar brimming with energy. It's not yet the full-fledged star we know today, but its immense heat and light begin to push back against the infalling gas and dust. This outward pressure eventually halts the collapse of the innermost part of the nebula. The protostar at the center continues to gather material and grow hotter. While the proto-sun blazes at the center, the remaining gas and dust flattens into a vast disk. This disk, called a protoplanetary disk, is where planets, including our Earth, will eventually form. Within this disk, a remarkable process begins, the process of accretion. Tiny particles of dust collide and stick together, forming larger clumps. Over time, these clumps grow, attracting more particles, gradually building up larger objects. This process of accretion transforms the protoplanetary disk from a sea of dust and gas into a well-defined system of planets. As the clumps within the protoplanetary disk continue to grow, they clear paths through the surrounding material. These growing objects, called planetesimals, represent the building blocks of planets. The inner region of the disk, closer to the Sun, is hotter than the outer region. In the inner region, only heavier elements like rock and metal can condense into solid particles, forming rocky planets. In the outer region, where temperatures are cooler, ices can also condense, allowing the formation of gas giants like Jupiter and Saturn. The story of the solar system is a dynamic and interconnected one, where the formation of each planet influences the fate of its neighbors. The early solar system was a chaotic and violent place. Planetesimals hurtled through space, their paths intersecting and colliding in spectacular displays. Earth, still in its infancy, was bombarded by these celestial projectiles. Each impact sent shock waves through the young planet, heating its surface and blasting molten rock into space. These impacts delivered water and other volatile compounds, essential ingredients for life, to Earth's surface. The bombardment was relentless, a cosmic hailstorm that lasted for millions of years, yet from this chaos order began to emerge. The constant bombardment, combined with the heat generated by radioactive decay, kept the young planet in a molten state. Imagine a world covered in a global magma ocean, a fiery sphere radiating heat into space. As Earth cooled, heavier elements like iron and nickel sank toward the center, forming the planet's core. Lighter elements rose to the surface, forming the Earth's crust. The early atmosphere was a toxic mix of gases, spewed out from volcanoes and delivered by cometary impacts. Yet even in this seemingly inhospitable environment, the seeds of life were being sown. While the inner solar system was characterized by the formation of rocky planets, the outer regions witnessed the birth of gas giants: Jupiter, Saturn, Uranus, and Neptune. These behemoths, with their immense gravity, played a crucial role in shaping the architecture of the solar system. Jupiter, the largest planet, formed early and quickly, its massive gravity attracting vast amounts of gas and dust. The formation of these gas giants had a profound impact on the distribution of smaller objects in the solar system. Jupiter's gravity acted as a gravitational shepherd, scattering asteroids and comets. The solar system, even in its infancy, was a dynamic and interconnected place. As the planets settled into their final orbits, a new era dawned. The era of intense bombardment subsided and the Sun, now a stable star, bathed the solar system in its warm glow. The early solar system was a place of both violence and creation, yet, from this maelstrom, a new order emerged, an intricate system of planets, moons, asteroids, and comets. The story of the solar system's formation is a testament to the power of simple physical laws operating over vast stretches of time and space, and it's a story that continues to unfold as scientists delve deeper into the mysteries of our cosmic origins. As eons passed, the reign of celestial fire gradually subsided. The early solar system began to find a semblance of peace. Earth's interior, still churning with the energy of its formation, continued to radiate heat into space. Volcanoes erupted, spewing lava and gases into the atmosphere. But as the planet slowly cooled, a profound transformation began. The molten rock that had covered Earth's surface for millions of years began to solidify, forming the first solid crust. Water, delivered to Earth by countless cometary impacts during the early bombardment, had accumulated in the atmosphere as vapor. As the planet cooled, this vapor condensed, forming thick clouds that blanketed the sky. Then, rain began to fall. It wasn't a gentle rain, it was a torrential downpour, a deluge that lasted for millennia. Water cascaded across the newly formed land masses, carving canyons, eroding mountains, and carrying sediments into the lowlands. Rivers formed, carrying the planet's lifeblood to the newly forming oceans. The oceans were not the pristine blue waters we know today. They were a murky, mineral-rich broth, a primordial soup teeming with dissolved chemicals and minerals leached from the Earth's crust. Volcanic eruptions continued to pump gases into the atmosphere and oceans, creating a dynamic and chemically rich environment. These early oceans, while seemingly inhospitable by today's standards, held the key to life's emergence. The dissolved minerals, the organic molecules delivered by comets, and the energy from the sun provided the raw ingredients and the spark for life's genesis. The precise details of how life arose from this primordial soup remain one of science's greatest mysteries. But somewhere in those warm, chemically rich waters, a remarkable transformation occurred. Simple organic molecules, through a combination of chance encounters and chemical reactions, began to assemble into more complex structures. These structures, guided by the fundamental laws of chemistry and physics, eventually gave rise to the building blocks of life as we know it: proteins, nucleic acids, and lipids. These molecules, in turn, assembled into even more complex structures, forming the precursors to cells, the fundamental units of life. This process, from simple molecules to self-replicating entities, represents one of the most profound transitions in Earth's history. It's a transition that remains shrouded in mystery, but one that scientists are actively exploring, seeking to understand the precise mechanisms that gave rise to life from non-living matter. The early life forms were simple, single-celled organisms, much like bacteria, thriving in the absence of oxygen. They harnessed energy from chemical reactions and sunlight, transforming the Earth's atmosphere and paving the way for the evolution of more complex life. The emergence of life marked a turning point in Earth's story. No longer was it just a rocky planet shaped by geological processes, it was now a living planet, its fate intertwined with the evolution of life itself. The stage was set for billions of years of biological evolution, a grand experiment in diversity and complexity. The story of Earth's formation is not just a tale of cosmic collisions, volcanic eruptions, and the cooling of a planet. It's also a story of water, of chemistry, and ultimately, of life itself. It's a story that reminds us that we are part of something much larger than ourselves, a cosmic tapestry woven from stardust and shaped by the same forces that govern the universe. And as we look up at the night sky, gazing at the stars that dot the darkness, we can't help but wonder if similar stories are unfolding on other planets, around other stars, in distant corners of the cosmos. The search for life beyond Earth is a testament to our innate curiosity, our desire to know if we are alone in the universe. The story of Earth's origin is a story that continues to inspire awe and wonder. It's a story that reminds us of the interconnectedness of everything in the universe, from the smallest atom to the largest star. And it's a story that continues to unfold as we delve deeper into the mysteries of our planet's past and search for signs of life beyond our pale blue dot. The Nebular Hypothesis, born from the minds of Kant and Laplace, has stood the test of time. It has been refined and expanded upon by generations of scientists, their work bolstered by increasingly sophisticated observations and computer simulations. We've sent probes to other planets, studied meteorites from the early solar system, and peered into the depths of interstellar clouds, gathering evidence that supports and enriches our understanding of this grand narrative. Today we can observe the formation of stars and planetary systems in distant corners of our galaxy, witnessing the same processes that gave birth to our own solar system billions of years ago. We see protoplanetary disks surrounding young stars, evidence of planets forming within these swirling clouds of gas and dust. The Nebular Hypothesis is more than just a scientific theory. It's a testament to the power of human curiosity and our ability to unravel the mysteries of the universe. It's a story that connects us to the cosmos, reminding us that we are all made from stardust, the remnants of ancient stars that exploded billions of years ago, seeding the universe with the elements that would eventually give rise to planets and life itself. As we delve deeper into the cosmos, driven by an insatiable thirst for knowledge and a desire to understand our place in the universe, we carry with us the legacy of Kant, Laplace, and countless other scientists who dared to imagine the unimaginable. Their work, a testament to the power of human ingenuity and our enduring fascination with the cosmos, continues to inspire and guide us. The story of Earth's formation is a story that belongs to all of us. It's a story that transcends borders, cultures, and beliefs, uniting us under a common sky, a shared history, a cosmic connection. It's a story that reminds us of our place in the grand scheme of things, a small but significant part of a universe teeming with wonder and possibility. As we continue to explore the cosmos, searching for signs of life beyond Earth, we carry with us the knowledge that we are not alone. We are part of a vast and ancient universe, a universe governed by the same laws of physics, a universe that gave birth to stars, planets, and the very elements that make up our bodies. And as we unlock the secrets of the universe, we gain a deeper appreciation for the preciousness and fragility of our own planet, our cosmic home.